Okay, let us solve question 6.4.4 from Arfken, Weber and Harris, and the book is Mathematical Methods for Physicists. Okay, so the question is, we are given the matrices Lx, Ly and Z. Okay, these are the angular momentum components which you can learn from the quantum mechanics, usually taught in the MSc first year. Okay, and from there we have to show that the eigenvalues of L square, where L square is represented as Lx square plus Ly square plus Lz square, the eigenvalues of this particular operator are positive. Okay, so over here I won't be taking up you through the quantum mechanical aspect by like putting the values of operators Lx, Ly and Z, or rather I will move around mathematical aspect and try to prove it in that sense. All right, so what we are given that Lx, Ly and Lz are Hermitian matrices. Okay, so Lx square dagger, we are doing this to check if Lx, Ly and Z square in their squared form are Hermitian or not. Okay, that is Lx dagger, Lx dagger, Lx dagger. So this is this one and this one is over here. So from the given definition of Lx, Ly and Z, so Lx square, so we can say that Lx square is Hermitian, and we can similarly say that Ly square and Lz square are also Hermitian. Okay, so we have done a little bit part of the question. Now we will go on to show the eigenvalues of L square are real and positive. So to show eigenvalues of L square are real and positive, for that we will just operate it on some random eigenvector of L square. Okay, so this beta is some kind of vector which is a common eigenvector for Lx, Ly, Lz whole square. Okay, so Lx square plus Ly square plus Lz square into beta equals to Lx square beta plus Ly square beta plus Lz square beta. Alright, now this would be alpha x square. Let's say these are the eigenvalues beta of Lx and alpha y square beta plus alpha z square beta. So that becomes alpha x square plus alpha y square plus alpha z square beta. Okay, now one thing that we must notice that Lx has been applied twice. So Lx beta is nothing but alpha x beta, and similarly for Ly and Lz. So we must note that alpha x, alpha y and alpha z, these are the three eigenvalues which are real, since the matrices Lx, Ly and Lz are Hermitian. So this is the property of Hermitian matrices, that their eigenvalues are real. So we must note that this is an important point to note over here. Okay, now what I have on right hand side is alpha x square plus alpha y square plus alpha z square beta. Okay, so these are some real numbers. All right, so sum of three real numbers would nothing be but a real number. Okay, alpha x square, alpha y square, and alpha z square, and they are sums. These individual are positive numbers because they are squared, and the sum of some positive numbers is nothing but greater than 0. So I will write it over here: sum of squares of a real number. Okay, from this we can conclude that eigenvalues of L square are real and non-negative. I hope this. I hope I can kind of explain you how the process went on in the mathematical aspect. Whereas when you go on with the quantum mechanical aspect, you will be using some eigenvalues of Lx as h cut L plus 1 something, and minus, and again something h cut L plus 1 m plus 1 L. This is 1 by 2. These are some, I'm not pretty sure right now, but these are kind of the eigenvalues which you will encounter if you go with that method, mm minus 1. Okay, so this is kind of a long and tedious process, plus this is way more complicated. So it's better we go ahead with the mathematical aspect and what we have learned in the chapter 6 of Arfken, Weber and Harris. Thank you.